density is the mass of fluid per unit volume. In the international system of units, density is expressed in kilograms per cubic meter. How the density changes with temperature for the fixed pressure. Let's see two fluids. One will be the most common liquid, water, and the other one will be air. Water. At 0 degree, we all know that density of water is 100 kilogram per cubic meter. What would happen for 20 degrees? Well, the temperature decreases. So slightly decreases. It's almost the same, 998. And at 100 degrees, density has decreased up to 958 kilogram per cubic meter. This has an impact on pressure losses and in the measurement of pressure. For example, it is not the same to measure the pressure of a pump with cold water than with hot water. We will see later how this is corrected when calculating the efficiency of the pump, for example. So we don't have to lose the perspective that although this variation is apparently not important, we should be aware that the variation of density with temperature for liquid is important for the reasons I mentioned. Regarding air, the density of the air at 0 degrees is 1.292. Please note that this value is 1000 times lower than the density of the water, and this has an impact on the consumption of power, pressure losses that are always higher in case of liquids. Due to this, the density decreases, as we see here, in a small quantity, but density behaves the same in air than in water. The variation of density is diminution of density with temperature. Regarding pressure, it is different because for gases, density is highly variable. So this is the reason why gases are considered compressible fluids. On the other hand, liquids in practice do not change their volume with pressure, so they can be considered as incompressible fluids. They do not compress. The specific weight, well, it is the weight fluid per unit of volume. In international system, the units of specific weight are of course the unit of force, Newton, and the unit of volume, cubic meter. The density and the specific weight can be related simply by gravity. It is a very useful relationship and frequently used with fluids. So the relation between the specific weight and density is expressed in this equation. So the specific weight is equal to density multiplied by the acceleration due to gravity. Other important concept is the specific gravity. For liquids, It is the ratio between the fluid density and density of water at 4 degrees. So what we have in this formula is density of fluid divided by density of water. For example, for gasoline, the specific gravity is 0.7, lower than water, of course. Kerosene, 0.8. Water, of course, 1. Mercury, 13.6. A very important property is the vapor pressure, because this property is closely related to the cavitation phenomena. So we should understand as much as possible what the vapor pressure is. It is an absolute pressure, not a gauge pressure. It is an absolute pressure at which a fluid begins to evaporate at a determined temperature. Think we are looking at a particle of fluid located inside the pump. For example, we are focusing always on pump. In case the local static pressure at any point of fluid is lower than the vapor pressure, what would happen? Vapor bubbles will appear, so the liquid evaporates. Let's see how is the behavior of the vapor pressure of the most common liquid for water in a cube. On the vertical axis we have the vapor pressure in bar. In the horizontal axis we have temperature in centigrade degrees. For a temperature of 0 degrees, the vapor pressure is close to 0. For a temperature of 20 degrees, the vapor pressure increases slightly. The same happens for 40 degrees. A higher increase is obtained for 60 degrees. A much higher increase for 80 degrees. And finally, a bigger increase for 100 degrees. We all know that the water boils atmospheric pressure for temperature of 100 degrees. Viscosity is another important property. It is a quantitative measure of a fluid resistant to flow. Let's think that we are moving our hand through a fluid, like this, where the movement is more difficult. Air with very low viscosity, water 50 times more viscous than air, or SAE30 oil that is 300 times more viscous than water. What is the answer? Of course, the last one, the oil, because it is a more viscous liquid. We have to keep in mind this when dealing with the flow of fluids, because the same happens when moving fluid through a pipe with a pump. The more viscous will be the liquid, the more power you will spend, the losses will be higher. In fact, Hydraulic Institute especially issued some standards to calculate or to determine how the viscosity affects the pump performance. There are two ways to express viscosity. The first one is dynamic viscosity, or simply viscosity, or even absolute viscosity. It is denoted by the Greek letter mu or mu. The units of viscosity in the international system is kilogram per meter second. In British system, a slug divided by foot second. In CGE's system is poise, that is equal to gram per centimeter second, and most used even is the centipoise, that is equal to 10 to the minus third power Pascal second. We have here a graphic showing how is the variation of viscosity with temperature for a fixed pressure, in this case the atmospheric pressure. Here in the lower part of the graphic, we can see how is the variation of viscosity with temperature. It is noted how for gases, when temperature increases, viscosity also increases. For liquids, the opposite happens. So we can see on the upper part of this graphic how viscosity diminishes when temperature increases. It's important to keep in mind this behavior, especially for liquid, when dealing with pumps, because you know that sometimes, for example, if you want to pump fuel oil, the first thing you should do is to heat the oil, to increase the oil temperature in order to get a lower viscosity to pump the oil in an easier way. There also exists the so-called kinematic viscosity, denoted by Greek letter nu or nu. It is the ratio between the dynamic viscosity and tensity. And this relation, for example, is used in Reynolds number. We will see the Reynolds number that is important when determining pressure losses.